So here we have a uniformly charged semicircular wire. The charge that this wire carries is Q. It's plus Q. So the wire carries positive charge. Uh, Only the semicircular part is the wire. The diameter that I've made is imaginary. So the diameter does not exist in the form of a physical object. Only the wire exists, and positive charge plus small q is uniformly distributed over the semicircular wire, and we are asked to find out what the electric field is that this semicircular charged wire, uniformly charged wire, creates at the center of the circle. So for that we have uh, made one diameter. Let us make another one, and at an angle theta measured from the positive x-axis, let us take a very small increment d theta, and let us first calculate what the length of this portion of the semicircular wire is. So let us say it has been given that the length of the semicircular wire is L, and if we assume that the radius of the semicircular wire is R, then we can say that L equals to pi r, where pi r is the length of a semicircle or the circumference of a semicircle. Then from there we can say that the radius is L over pi. Okay, so we know from math that the length of this portion is r d theta. So we can say that d of L, or the small length, is r times d theta. And we know that r is just L over pi, so we can say that the length of this portion is L over pi d theta. Now we have been told that charge has been distributed uniformly over this semicircular wire. So because this is a uniform charge distribution, we can figure out quite easily how much charge is contained in this small portion, in this small length of the semicircular wire, infinitesimally small length of the semicircular wire. So that charge, by simple unitary method, we can say that uh, the total charge is Q, and charge per unit length is Q over pi r. Therefore, the charge in this portion of the semicircular wire is Q over pi r, that is the charge per unit length, multiplied by the length of this portion, which we know is dl. So this is the small charge dq that resides in this portion of the semicircular wire. Or we can say that dq is Q over pi r multiplied by dl, but we know that dl is just L over pi times d theta. So we know that the small charge dq is QL d theta over pi squared r. So to repeat, how did we find out what dq is? And what is dq? dq is the charge that is carried by this portion of the semicircular wire. dq is charge per unit length multiplied by the length of the small segment whose charge we are interested in finding. So this is what dq is. So now we can figure out how much electric field is created at this point due to this small charge dq. So let me make the diagram one more time. So say this is the portion of the wire we are interested in. This carries a charge plus dq and it creates an electric field, say dE, in this direction. Why in this direction? Because this is a positive charge. Positive charge creates an electric field always away from that positive charge. And why dE? Because the charge that creates the electric field is small. Therefore, the electric field in turn must itself be small. And from the formula for electric field, we know that the electric field is 1 by 4 pi the permittivity of free space epsilon naught times the charge that has created the field divided by the square of the distance between the charge and the point at which we are finding the electric field. In that case, that is the radius. Now we know what dq is. We'll substitute it, but before substituting the expression for dq into the expression for electric field, we'll have to figure out one thing. Say this angle is theta. Actually, this angle is theta because it is vertically opposite to this angle. And if we split the electric field into its components, we get a component dE cos theta on this side and another component dE sin theta on this side. Had we taken our element at an angle theta measured from the negative x-axis, this would have been our element containing the same quantity of charge dq, and it would have created a small electric field in this direction dE, and this angle would have been theta. And had we resolved this dE into its components, we would have got a dE cos theta on that side and a dE sin theta on this side. So the dE cos thetas would have cancelled each other out and we would have got only the dE sin theta component to be the significant component. So in that way we can say that if we integrate the contributions of the electric field on both directions due to each of the elements over the semicircular wire, throughout the semicircular wire, then these components, the components over the x-axis, will always cancel each other out and we'll be left with only the contributions along the negative y-axis. So the net electric field at this point, due to the entire semicircular wire, will be the effect of adding up the contributions of the dE sin thetas only. So we'll say it's integration dE sin theta. And because we are integrating over theta, our theta will go from 0 to pi because we start out over here and then we rotate 180 degrees to cover the entire semicircular wire. Now note that, okay, I'll say that later. So first let us evaluate what this is. So this is integration from 0 to pi dE. What is dE? We know what dE is from the previous line. It's 1 by 4 pi epsilon naught dq over r squared sin theta. So that becomes integration, okay, 1 over 4 pi epsilon naught. We know what dq is from here. We'll substitute the expression for dq, ql d theta over pi squared r. We have an r squared, another r squared at the bottom, so this becomes r cubed sin theta, and we are integrating from 0 to pi. We'll take all the constants out, so that becomes ql over 4 pi cubed. There's a pi here, a pi squared here, so that becomes pi cubed, r cubed, this r cubed, epsilon 0, and within the integration from 0 to pi we are left with sin theta d theta. So what is integration of sin theta d theta? that's just minus cos theta. So this expression now becomes QL over 4 pi cubed r cubed epsilon naught. And what are the limits after integration? The limits after integration are from 0 to pi. If you put the limits, if I substitute the limits directly, I'm just skipping one step due to slight lack of space, that will become cos 0 minus cos pi. So let me write that down, cos 0 minus cos pi, which is actually 2. This 2 will cancel this 4 and we'll get a 2 in the denominator. So the final result is QL over 2 pi cubed r cubed epsilon naught. So this is the value of the electric field that is created at the center due to the semicircular uniformly charged wire. But what I wanted to say was, if we say, what many students do sometimes is that they'll say that the expression for electric field, instead of being integration dE sine theta, it's integration 2 dE sine theta. But in that case, we'll have to integrate from 0 to pi over 2, because if we write 2 dE sine theta, that means at each instance we are counting the contributions from two elements. So we'll only have to turn half the circle. We'll only have to, half the semicircle. So that's it. So we have figured out what the expression for electric field is due to a uniformly charged semicircular wire at the center of the wire.